Hi everyone. In this video we are going to solve a very important differential equation in the field of physics and engineering differential equations called the heat equation, and we're going to do that using what we've discussed about Fourier series. Alright, so let's get at it. Let's take a look. The heat equation. Well, what we're going to do is we're going to imagine a thin bar of uniform density with length L. Right? So imagine just a wire, a metal wire, okay? And the heat equation is going to describe the dissipation of heat through the bar over time. So it is given by this differential equation. Now, we are using subscripts here to denote the derivatives. So this subscript t denotes the derivative with respect to t, and these subscripts x represent the derivative with respect to x. U is a function of two variables, x and t. So that makes sense. And these are partial derivatives. What does U measure? U describes the heat at position x, so some position along this between 0 and L, at any time t. And A is some constant describing the thermal properties of that bar, how fast we could expect heat to dissipate through it. If it's metal, we expect heat to dissipate very quickly because metal is a good conductor. If it's something else, like wood or something, it might dissipate a lot slower. So that'll be taken account of by this constant A. All right, well, the heat equation is typically described with boundary conditions. One possible set of boundary conditions may prescribe the initial distribution of heat throughout the bar, given by some function f of x, and also the heat at the ends of the bar going forward into the future. So we're just going to regulate the heat at the endpoints. So the initial distribution of heat throughout the bar is going to be given by this function f of x, as we said. So remember that u of x is a function of x and t. So what we're saying here is that when t is 0, u of x is just equal to this function f of x. That's going to be the initial distribution of heat. And so this is an example. We might have defined f of x to be this function here. All right, so this is how heat is distributed. So it's kind of warmer in the center of the bar, and we're keeping it at temperature 0 at the ends of the bar. And so the heat at the ends of the bar, as I just said, we are keeping at 0. Now, this is one setup. This is not the only setup for the heat equation. We could specify different boundary conditions. All right? It's one thing you could do is just have these boundary conditions be free, so that you aren't specifying anything in particular. You could also specify that the heat has to match up on both sides of the bar. Now, why would you do that? Well, that's what you would do if you were measuring the bar as actually a loop. And so then we demand that the heat match on the other side, but we don't necessarily know what it is. We just need to know that it matches, so that we would imagine that that would have to happen if the bar was looped around. You wouldn't have a discontinuity in the heat. All right, so there's different boundary conditions you could set here, but these are the ones we're going to focus on in this demo. Now, so we have the initial distribution and the heat at the ends of the bar. Now, as we let t go forward in time, what we're going to see is the heat dissipate out. Now, since we're regulating the heat to be 0 at the ends, all the heat's going to flow out to those endpoints. It's just getting kind of sucked out of the bar. But this is, as time goes on, this is what we expect to see. The heat should diminish. And this solution to this differential equation will tell us exactly how it diminishes. So we know at any time and in any position what we can expect the heat to be. All right, so we need a strategy to solve the heat equation. And here's what we're going to do. We're going to make a rather wild assumption here. Okay, we're going to assume that our function of two variables can be expressed as a product of two functions, y of x and z of t. This may seem like an unreasonable assumption. Why can we get away with this? Well, we'll see that even though it seems a little wild, in the end, it's going to produce something that makes a lot of sense. So we're going to start with this assumption. Now, if we do, then if I just substitute these in place of u in this differential equation, well, on the left-hand side, I'm taking the derivative of u with respect to t. That's just going to be z prime. Y doesn't depend on t, so it doesn't get a prime. So I just get y z prime. And on the right-hand side, I'm differentiating with respect to x, so that's only going to affect y, because z doesn't depend on x. So I just get the 2 primes on y. Okay, so what I'm going to do is divide both sides by a squared yz. Right. I'm going to collect the y's on one side and the z's on the other. So I'll cancel some terms here, and there I have. I've collected all the z's on one side and the y's on the other. Now this is interesting because the left-hand side, remember a is a constant, so this depends solely on t. And the right-hand side depends solely on x. Now, if you think about what that implies, if I were to vary x, this doesn't depend on x, right? And if I were to vary t, this doesn't depend on t. So that must mean that both of these are constants. Right? These have to equal the same constant. And I'm going to call that constant negative lambda. Okay, so there we go. Each quantity there has to equal negative lambda. Okay, so let's focus on that differential equation for y. What we're going to do is we're going to just rewrite this in a different form. Okay, so I'm going to multiply both sides by y of x. Cancel those out. So now I have this. I'm just going to add lambda y of x to both sides. There we go. All right, so we have this differential equation. But remember, we also have these boundary conditions. Right? These boundary conditions are saying that the temperature at the left end of the bar and the temperature at the right end of the bar are both 0. And it doesn't depend on t. It's for all t. For every t, those are equal to 0. Well, those translate into boundary conditions for this differential equation. We're just saying that y at 0 and L are equal to 0. Okay. Okay, so this is the eigenvalue problem that we talked about several videos ago. Okay, so we know exactly how to handle this. Remember that we figured out that the eigenfunctions are these functions right here. These are the solutions to this differential equation. Of course, they only solve the differential equation, as we showed, when lambda has this form, n squared pi squared over L squared. So this is the solution to the eigenproblem. We found the solutions and what the lambdas would have to be in order to produce those solutions. And these are all valid provided n is an integer from 1 to infinity. And those are all the solutions. There's no other possibilities. Okay, so now let's go back to that differential equation we had for z. Okay, it looked like this. Well, I'm just going to multiply both sides by a squared z. Cancel those off. Solve for z prime. All right. That differential equation there corresponds to a solution of this differential equation with the same lambda. Right? Remember, we had both of those equal to negative. We had a few slides ago, we had both of those equal to negative lambda. That's the same lambda. Those weren't different constants. Those were the same constants. So that means that these lambdas that we produced when we solved this eigenvalue problem have to be the same lambdas that work here. So this lambda up here has to be of this form. Okay, so that's what we're going to put in there. Put lambdas, and I'm going to call the lambdas of that form, I'm going to call them lambda sub n. So there we go. I rewrote it with lambda n in place of lambda. So I'm just imagining anything of this form. So we're just looking for solutions to this. Well, this is super easy to solve. This is just a first-order differential equation, and so when you solve it, you get this. Now, let's just express lambda n out a little bit there. Remember what it was, just substituting that stuff in there, and so that's it. Now, you might be saying, well, wait a minute, what about that arbitrary constant that comes out? Well, yeah, if you wanted to write down the most general solution, you would put a constant out front here. That would also solve this, right? But we don't need to do that because, remember, the final solution that we're writing down, u, is a product of z and y, right? So if there is going to be a constant, we can just take care of it by including it in y. So I don't need to write it here. Since we're multiplying this by y, y will take care of what that constant is. Okay, so we have shown so far that this function, written as a product of y and z, and if we take any of those solutions that we found, yn, zn, if we multiply those together for any n from 1 to infinity, that will solve this boundary value problem. Now you should be saying, well, wait a minute, where is that other boundary condition? What about that last one? Well, I got to be honest here, there's no reason that should solve that boundary condition, right? It solves these, right? That's what we used when we were solving these differential equations. We used this one when we solved for y, but we never used this. There's no reason that this should satisfy this. We had done nothing with that function f. So there's no reason that this should have taken account of that. So that's something we need to deal with. And that's where we're going to need Fourier series. Now I'm going to get out of the way because I need to show you how excited I am. All right. Oh, good. We get to use our Fourier series. Terrific. So we need to use these solutions that we came up with to generate that function f of x when time is 0. We need the solution to equal f of x when time is 0. Okay, so moving back down. I'm getting dizzy here. Generating f of x. Since the differential equation is linear, any linear combination of solutions will also be a solution. So if I take constants alpha 1, alpha 2, alpha 3, multiply them by my solutions, y1, z1, y2, z2, y3, z3. Remember, all those were solutions. Well, if I multiply them by constants, they'll still be solutions. And if I add them together, they'll still be solutions. You can check that. Multiply a solution by a constant, plug it in, you'll see it still solves the differential equation. Take two solutions, add them together, plug it in, you'll see it still solves the differential equation. So I could just add a string of these together, and it'll still solve the differential equation, provided it converges to something. And that's something you have to be a little bit careful of, and I'm not going to go through those details. I want to keep this video simple, so I'm going to brush over that. But that is something that's very important that you should consider, and it's written in, if you look in your book, you'll see they explain what to do about that convergence issue. So we need to define these constants, alphas, these alphas. We're going to have to try to pick these so that our linear combination converges to f of x at time 0. All right, so notice that our functions z, they're all equal to 1 when t is 0, because they were e to the something times t. So if you plug 0 in for t, you get 1. So those things are all equal to 1. So those kind of just go out of the equation here. They're not even really, they don't really matter. So really, if we need this stuff to equal f of x when t is 0, we just ignore the z's. They're all equal to 1. I just need this sum to equal f of x. Well, just writing that out, remember what the y-n's were. The y-n's were these sine n pi x over l's. Okay, now these coefficients here, these are what we got to find, but we know how to find these so that this thing is the Fourier expansion for f of x. We know exactly how to do that. We discussed that in the previous video. These are the Fourier coefficients. Those are the Fourier coefficients. So how do we find the Fourier coefficients? We have a formula for that. There it is. Looks like a really ugly formula, but remember what we talked about. All this really is, maybe if I go into this corner, I'll be safe. All this really is it's the projection coefficient of f of x onto this eigenfunction. So remember we talked about how you can project vectors onto other vectors. You can project functions onto other functions. Well, when you do that, you just get a multiple of the original function. This is just that multiple. So we'll just, if you go back and look at that video, this really, when you think about it that way, is not that bad. This is just the projection coefficient when we project f of x onto that function. Now, you can simplify this a little bit because you can evaluate this integral at the bottom. And you'll see that that just converges to L over 2. That's just equal to L over 2. So I can just rewrite this like this. Dividing by L over 2 is multiplying by 2 over L. All right, cool. So those are my Fourier coefficients. And oh, look, the lighting changed. That's the magic of video editing. So moving on. The Fourier expansion for our function f of x is given as follows. Now notice I'm writing a squiggle equals here. Okay. The reason I'm not writing an equal sign is because we have not verified that this series converges to our function. This is the expansion, but one extra step, that's an important step that you'd want to make in these problems, is to verify that the series actually does converge to the function that we were working with. I'm not going to go through those details in this video, but I want to point out that that is an important step. Okay, so in summary, the solution to the boundary value problem, as we had laid out, is given as follows. Here we are. Alpha n's are just the constants that we described in the last slide. The yn of x and the zn of t. Well, yn of x, in our case, is given by sine n pi x over L, and zn of t is given by e to the minus n squared pi squared a squared over L times t. All right, so this is the solution to the boundary value problem. Again, considering the fact that it converges. Okay, so we have to verify that that does converge. And those constants alpha n are given by the formula that we derived. Now, let me also point out that what you're seeing here is dependent on the boundary values and also the interval that we're working with. If you change the boundary values, or the boundary conditions, we may not be just specifying the values of u, we might be specifying the derivatives of u. If you change these conditions here and you change the interval, some of these things can change, all right? But the steps that we went through in this video generally play out the same way. So I think what's in this video is sufficient enough for you to go through and make those adjustments on your own. You should see where things will change and how to change them. Okay, so that is it. Solving the heat equation using Fourier series.